Alright, let's get started with the first problem of the day. This is going to be LeetCode number 143, Reorder List. You're given the head of a singly linked list. The list can be represented as so. Reorder the list to be on the following form. Okay. So you kind of want to interweave those like so. So 1 and then 5, then 2, 4, 3. Okay. Interesting. So given that it is a linked list, there's probably some sort of two-pointer approach, maybe, where we swap elements such that by the time that we hit the end with our pointers, the swaps are in the correct spot. Could be wrong about this. It may not end up being a two-pointer approach, but I think that that's the most sort of general idea. So let's take this 1, 2, 3, 4. Let's take this basic linked list and let's kind of play around with it and let's see what we can come up with. Well, we know that the 1 in here stays in place. But what happens if we swap, let's say, for example, 2 and 3? If we swap 2 and 3, and let's just assume that it works as usual. And then we move on to the next pair and we swap 4 and 2. It's not quite what we want. Ultimately, we want the last element to be in the first or in the second spot. Unfortunately, because it's a singly linked list, there's not really a way for us to do so in a very easy manner. Because we can't go backwards from the end, right? If we could go backwards from the end, then this would be a relatively simple problem because we can just take like the 2 pointers and then move one right there and then set it to the next one and then move you forward and then move you to the next one and then move you forward and so on and so forth. Like, it would be a little bit more straightforward. But unfortunately, that's not the case. Which is what leads me to believe that there is potentially a solution where we swap the elements in a different way. Now that I think about it, what if we space them out a little bit more? So now what if we had the left pointer here and the right pointer here? Let's say skip the head of the list. Then we go here. Then we swap 2 and 4. Then we swap the last 2 elements. So we swap every other pair, and then we swap the last set of elements. That gets us what we want, but I'm not sure if that will get us to where we need. Let me think about this. Because ultimately we want to swap with the last element. So that means the second element moves over 1. The third element would need to move over twice. And the third element, let's see. First element doesn't move. Second element moves once. The third element doesn't move twice. Oops. Let's do... So the result we want is 1, 5, 2, 4, 3. So first element moves 0. Second element moves 1, right? We go from 1 to 2 to 1 to 5 to 2. Third element moves, well, we go from 1 to 2 to 3 to 1 to 2 to 1, 5, 2, 4, 3. So it goes here. It starts here and it moves over 2 times. I wonder if this pattern persists. So does the fourth element move over 3 times? Well, assuming that there was a third and then a fourth element here. Well, the fourth element in this list does not move actually at all. But the fifth element does. But this is, we could also consider this as the second from the middle, right? Maybe there's something to do with the middle of the linked list. That's an interesting idea. What if we split the linked list? And we reverse the other half? Then we combine them in place. So split the linked list in 2 and reverse the other side. Then use a 2-pointer approach to recombine in place. So now we go 1, and then we go 5, which goes to 2, which then goes to 4, which then goes to 3. This makes sense, but what does this algorithm actually do? So given 2 heads, we start by adding the next of the current or original to the, by setting the next of the original to the next or to the head of the reverse. And we want to keep a temp pointer on the next of the reverse head and temp pointer on the reverse on the next of the original head. So 2 and 4 in this case. Then set the head of the reverse next to the original temp next, so 2. So this sets the next to 1's next to 5. This sets 5 next to 2. Then we set the head to the temp, the original temp next, and set the head of the reverse to the reverse temp next, and we repeat. Okay, I think that's a pretty solid plan. How do we deal with the if we don't have an even number though of nodes? Let's see. If we do the same thing, then we'll set 2 next to 4. We'll set 4 next to 3. Head then will be set to 3, and reverse next will also be set to 3. Okay, interesting. So we can maybe do a condition of while head is not equal to reverse here as a stopping condition for when there is no more. Well, let's see what happens if we had a 1, 2, 3, 4, that type of situation. Well, where does the middle of the linked list actually go? Does the middle of the linked list, I forgot if it, let's assume that it's right biased. So it says that the middle of the linked list is actually this 3, not this 2. Right, because let's assume that if we had a regular pointer here and a fast pointer here, when we get to 2, then the fast pointer will be at 3. When we get to 3, then the fast pointer will be off, so the middle will be 3. Okay. So when we do this, we first set 1's next to 4, then we set 4's next to 2, and we set the head to 2 and the reverse to 3. Since they're not the same, then we set 2's next to 3, 3's next to 3. Maybe a condition here that while the head next is not the reverse, so that we don't set a sort of infinite loop here. Though in this case, I suppose it's not that terrible. We could set head to 3 and reverse to 3 in the next iteration, and then that will trigger. So I guess it's not a big deal if we don't actually end up adding this additional condition here. Of course, to find the middle of the linked list, this will take O of n time. Technically half of that, but you get the point. Then we get reversing the linked list. This will take linear time as well. And then moving the pointers around will also take linear time. So in total, this algorithm will take linear time and constant space, because we don't really need to hold on to any additional nodes beyond what we already have. So let's get started. So let's start by actually creating our helper functions. So middle linked list, which takes a head, which is nullable, or non-nullable rather, and returns a non-null list node. We'll take a reverse linked list, which will take a head and also return. We'll also return that. So now we can say, okay, so let's start by, so this finds the middle of the linked list to reverse from. So we can say var slow is equal to head, var fast is equal to head, while fast is not next, or is not null, and our fast next is not null either. Slow is equal to slow.next, and fast is equal to fast.next, question mark dot next, and we will return slow. And the reason why we do this is because we might end up, by moving two at a time, we might end up at the last node instead, which is perfectly fine. Yeah, and I think that's pretty much it for the middle of the linked list. Then we can say var current is equal to head, while our current is not null. Val next is, or temp next is, well, what we'll do is that we'll say var next is equal to head.next. While our next is not null, we'll say our temp next is equal to next. Next is not null, but our next value of next might be null. We will say our next.next is equal to current. So now we've flipped it. And let's see. Think about this some more. Actually, you want a regular and a slow pointer. Is going to be current.next. Current.next is equal to slow. And then current is equal to temp next. And if slow is null, and this should be a list node nullable. This is also a list node nullable. If slow is null, then slow will be set to head. Else slow is equal to slow.next. And then we can return, because current would be null at this point, it's set to slow. So the idea is that we have a regular pointer and a lagging pointer. We set a temporary to the next value, and then we say, okay, this current node, the next is a previous node, and then we jump over, you jump over. And since you're at null, then you jump to head. Actually, we want you to jump to where current is right now, as that's the most recent node. And then we want to set our current to whatever was next. Right. Because then we'll have that set to there. You first go to here, you then go to there. Then you'll set your next and current next to slow. Then slow goes to current, because the next would be that way. So you go to the current and you go to the temp next. Okay, yeah, so that works. So reverses the linked list when called on a half, splits the list in half. So now we'll say that val or var reverse head will be equal to, we want to reverse linked list from the result of middle linked list, which takes head. And of course, if our head is equal to null, then we just return, because if our head is blank, then there's no point. And also, if our head dot next is equal to null, then of course there's also no point because it's just a single item. And also realistically, if our head dot next is also null, then there's no point, because if there's two nodes, also doesn't matter because it's already in the order that we need. It's only when you get to the third node that things start to get hairy. So now we have the reverse head, and of course we have the regular head, and we'll say original head. And we'll say while original head is not equal to reverse head. We'll go through our algorithm. So we'll say val temp original next is going to be original head dot next. We'll say our temp reverse next will be equal to our reverse head dot next. Then we'll say that our original head dot next is equal to reverse head. Then we'll say that our reverse head dot next will be our temp original next. We will then say that our original head will be equal to our temp original next, and our reverse head will be equal to our temp reverse next. So again, the idea is that we have our original, we set the next of the original to the reverse. We then set the reverses next to the temp next. We move our head next to the temporary next. And then we finally, at the end, we move our temp or our reverse head back to the next of the original reverse head. And then we repeat until we get to the end, until we get to the point where we don't need to reverse anymore, and that is when original head is equal to reverse head, and that will happen whether or not the list node is even or whether or not it's odd. Let's see. This should not be a nullable list node. This should not be a nullable list node. I think we're fine here. So again, the idea is that we first split the list in half, and we get a second pointer at the end of the list, and we go from there and use a two-pointer approach. Let's go ahead and run the code, and let's see where we end up first. Maybe there are some compiler issues that we need to take care of. So slow is, let's see. Slow should not start, or should not be a list. Slow should never be a null pointer. So let's do the double bang operator here. Although this is a little bit wonky. So maybe we can do a list node nullable here, as much as I don't want to. So this is now a list node nullable, and this is a list node. Should be a list node because we've already established that if head is null, we just return. Fast is equal to fast.next (next). You are inferring that head is a list node. So in fact, in this case, let's make you a list node nullable. We know that the original head Still looks like it's nullable. Let's see. And original head dot next is equal to reverse head. And that should be it. Let's go ahead and run this again and let's see where we end up. Looks like reverse head. Right, reverse head is now nullable, so let's go ahead and clear up those issues. Let's go ahead and see where we end up now. Looks like it works for the first example. Let's go ahead and throw in a second example with an odd length linked list. Looks like that works as well. Let's throw in some weird ones. So let's do 1, 1, 2, 1, 2, 3, and finally an empty one. Let's see how this performs. Oh, looks like we have to have at least one element in our test cases. So let's just throw in the first 3. Looks like they work. And realistically, since the problem statement says that there has to be at least one node in the list, this is kind of a no-op right here, if head is equal to null, but we'll keep it in there. Let's go ahead and run this code and let's see where we end up. Alright, looks like it's a pretty standard type of answer. I think that this is actually a pretty good place to stop for this problem. I'm pretty happy with the solution myself. It was relatively intuitive once you kind of took a look at the potential options in terms of what you could do with a linked list and sort of how you could approach things. I really like these linked list types of problems though, to be honest, and especially this one as well, because I feel like a lot of the linked list problems make sense from a type of mastery learning perspective. I just really love that a lot of the harder linked list problems really come down to whether or not you know how to construct algorithms from the simple linked list operations. Do you know how to reverse a linked list? Do you know how to find the middle of a linked list in terms of singly linked lists? And so on and so forth. And you kind of construct the solution out of the basic building blocks. And that's what I really love about linked list problems. In any case, I hope you learned something, and I'll see you for the next problem.